Okay, so in today's agenda, we're going to be talking about keywords, the keywords that Java needs to execute and to run. We're going to be talking about the data and how we define variables, what kind of primitive data types are, and what are those. We're going to talk about variables and I already said variables, data types, arithmetic expressions, and logical operators. So let's then get started. What are Java keywords? So keywords are words that we can't that we cannot utilize in our program. In other words, we cannot name a variable continue or new or final or void. Any of these keywords, these are reserved for the computer. The computer actually understands it. So let's assume that we have a list, right? 10, 12, 5, 6, 4, and 35. So we have that list. And if I was going to ask you, well, how do you do it? If we went to do that algorithm where we are looking for the smallest number and then going to the next one, etc., probably the algorithm would look like something like this, where we are saying, okay, we go through this number. Is this the smallest? Well, let's assume that we still haven't seen the rest. So right now, the smallest number in the list is 10. Then we go into the next number. Let's erase the pointer. And then now let's go into this guy. So which one is the smallest between 10 and 12? Then it would still be 10. Then we go into the next number. Which one is the smallest between 10 and 5? It would be 5. So then that one is the new smallest. Then between 5 and 6, 5 is the smallest. Then between 5 and 4, 4 is the smallest. So we replace it. And then between 4 and 35. So then if we try to make this algorithm, then the next iteration would be, okay, well, because now we know because we found that which one is the smallest on the list. Now we have to go and do the same algorithm again to see where the 4 is, so that way we can eliminate it from the list, right? I mean, we do this at an incredible speed in our minds. Granted, there are very, very, very good sorting algorithms out there that are super fast and don't require this, but I'm going with a very simple algorithm that would allow beginner programmers to more or less understand the process in their mind. So we're not going for the most efficient algorithm right now. It's more like for the most logical one. So then we go through the list and we start finding which one is the next smallest. And we find that one and we remove it. Then we go to the next list. So you see how many times I'm going through the entire through the entire list to try to find the numbers. So just so that I can build a list that is sorted. Now, at some point, I have to name some of these variables. Like, for example, if I have a copy of the list, once we were at this step of 10, 12, 5, 6, 4, and 35, if we have this list again, which is the original one, and at some point we want to make a copy that doesn't have the 4, a copy that does not have that 4, then we would most likely, if we were not careful about keywords, most likely we would call that the old list. I mean, the one that we're dealing with. We would be like, oh, this is the old. And the keyword old is not really in here. I mean, there's no keyword old. You can see L, N, N, P. There's no keyword starting with an O. So I lost this guy. So because we are not in that old keyword, this one would be a valid variable name. Close this window. But then the new list that we would be building, if we wanted to stay consistent with this naming, this guy would not work because new is this guy. It's in the list of protected keywords. So most likely, if we did, let's say, int old equals 4 or 5, and said int new equals old, we are going to get an error, and it's saying identifier expected. And you can see that the error that the compiler is giving you here, and I want to highlight at this part where my cursor is, that little pop-up that came in. The error that you are getting is not user-friendly enough, that it's telling you are using a keyword where you were not supposed to. Because the compiler is expecting that you would have a data type right after, or a class right after, or an object. So be careful with some of those things. Just know that when you are using a keyword, you might get like really weird names. So, really weird messages. So how do you go around creating a variable name when you still want to use new? Well, a good example would be to add an underscore or a different character before that keyword. And then now you have a variable that looks more readable. You would understand that new is related to the old. Actually, it would be even better if both matched, so that way you understand that they're kind of related. So anyway, point is that keywords are reserved for the computer so that you can put those as statements in your code, like if or double, or even, where's int? If int right here. So anyway, I think we need to start a little bit before that and understand the basics and what is the basic terminology for the code. That way we can communicate with other programmers and understand things better. One common thing that people keep talking about or keep bringing up is the concept of lines of code. And while that is very intuitive for developers talking about their programming experiences, by all means and purposes, lines are really not a thing in a lot of languages. So you're going to be like, wait, what does that mean? If I told you that each instruction on a computer lives on one line and one line only, that would be a lie. I would be telling you an absolute falsehood, because an instruction for the computer is known as a statement. And in the case of Java and other programming languages like JavaScript, C#, C++, C, even PHP, well, PHP, they dropped this requirement, but they add a semicolon at the very end of each statement. So if you see in this part that is statement 1, this full statement is taking 2 lines rather than 1 line. And that's why I included that, because I want you to understand that a statement is an instruction to the computer that can go even beyond a single line, because the compiler will look for, okay, there's a semicolon. That's when the new statement starts, and it will finish when I see another semicolon. Okay. Then if we understand that a statement is an instruction of code that we are sending to the program, then what would be a collection of code? That collection is known as a block. And a block is defined by anything that is surrounded. In the case of Java, in other languages is different, but in the case of Java, a block is essentially zero or more statements. Zero, it's because it's not really necessary for it to a block of code for it to have code, but zero or more statements surrounded by the curly brackets. So, for example, this function, this entire thing in this slide is a function, and this entire thing is one block, and this entire thing is another block. So you can have a block that contains other blocks, but as long as it's enclosed by these curly brackets, it's a block of code. Now that we understand statements and blocks, let's talk about variables and the scope of a variable. In Java, we define variables by putting the data type that variable is going to hold, the variable name, and an optional value assignment. That's basically how we are going to define those values. So, for example, in this case, if we did int my variable equals, 10, this is how we define this variable, even though there's a warning that we're not using it, which is correct. Once we declare it, we're never really using it. We can also leave it like this, and that's enough. When an object is assigned a value of 0, meaning, I'm dropping my Apple Pencil. When there's a value of 0, and let's go back to the whiteboard. Let's assume that we have these, int x equals int x. It's going to essentially assign it to a 0, just like by doing like that. Why? Because we are allocating a block of memory, and I'm going to probably find another color here to draw. Let's go for a lighter color. These are kind of like the bits, just assuming that there's no bits that are on. If we were going to assign a value, for example, a 1, we would turn on this byte, and then now we would have a value of 1, right? But if it's 0, that means that everything is off. Everything in this case would be off. So we would have, where did I put that color? Is it this one? This thing's gonna, no, I'm not writing. Okay, so it would be empty. Now, in the case of an object, and we're going to get into this a little bit further in, object. Equals, if we, actually without the equals, if we did this, basically we would allocate the memory where the object lives, and we would have all the bytes turned off for that object. And once all those bytes are off, basically, because an object cannot really be 0, even though that internally it's a 0, the computer, whenever it interprets an object that it has a 0 value, it considers it a null value. My handwriting is horrible here. So so even if it's a string, I think that a string, I don't remember. Let's do an exercise. If it would build it as a single empty thing or a null, we should probably test it. Anyway, moving on with this. Now, let's talk about then what is the scope of a variable. The scope, well, in the previous class, we were talking about how Java does memory management by itself. And as one of the reasons why it's secure and why it's a good programming language. So if it does memory management, that means that if we create any object, and let's go back to this. Let's assume that we create this object, and let's just represent it by this circle, right? So we're creating this object, and then later we stop using it. And then we go ahead and create another object. We go create a couple more objects, and and then we stop using them. And then we create a bigger object, and maybe let's say also some other bigger objects all over the place. The more we're utilizing the memory, we're gonna get the memory full, and we're running in the risk of not freeing enough memory. Like, for example, if we're creating objects, and the first blue was the first pass, and the red, then the black, and the ones that are in like that greenish gray. But let's assume that we're going to create another. Let's grab this soapy color, this Tiffany color, and we're trying to add more objects into our memory. Now that we've got all those objects, if we wanted to add a big object in this screen, we can't, even though that technically in our timeline we have stopped using some of these objects. So at some point, Java needs to be smart enough to be able to delete objects that are not being used anymore, so that it can make room for new objects, so that you're not running out of memory. So, hidden Mickey. So because we don't want to saturate the computer with that, we're going to start removing some of those objects by itself. So the way that Java knows and understands that something is not being used is via the scope of a variable. And the scope is nothing else other than defining when a variable is declared and when a variable dies. So let's assume that let's copy this code that isn't in the slide here. Let's just put it inside here. And let me remove all these numbers. Okay, so we're gonna see that first of all, there's some errors. First of all, the code is expecting an int and it's giving it a float, but let's give it a float, and let's just change this so that way. A scope is basically every time that you declare a block, this variable is going to live in that scope once it's reading from top to bottom. Let's assume that we create a variable right here, and we say like we have int x, int y, and int z, and then we start playing, we call a function, and we do function z. We're going to call that function, and then do another block if x, and then we're going to put z plus plus, something like that. Z is going to live all the way down to here, from that point that it was declared all the way down. Y is going to live from this point all the way till the end of that block that it was declared. X same thing. Let's put a yellow for X. So this is X, this is Y, and this guy is, and this guy is Z. So you can see how a variable that, if we want to reference Z right here inside of that, if we want to reference Z inside of this other block, it's going to be respected because this is a child of the parent block. If we were going to say int A and C++, and then later after that block, let's remove this guy here. Let's say that we want A to be copied by 1. What is the current, I don't want to say life expectancy because it sounds weird, but what is the current expected scope? Let's even put some numbers down here so that way we can see 2, 5. So each one of these guys belongs to a different line of code. So if I asked you, what is the current scope of A? Can you guys tell me from what line to what line it would live? A does not live here, cannot live here. So we're going to get a compiler error because it's going to say that A was not declared. However, and let's find a different color. Let's use this. Let's maybe make it into a bright pink or a purple. A was declared from here. A was declared from here all the way down to here. So it's 6 through 8. So again, the compiler is going to complain here, which is exactly what we were seeing here. Once we see this variable inside scope equals 10, and then outside scope is going to say it cannot resolve the symbol. And so don't be tricked because you can see it in the same line. Doesn't necessarily mean that you know that the computer can see it, because once the computer went through these 2 curly brackets, inside scope, this variable name inside scope goes out of the window. All right, so now that we understand then variables, I want to talk about primitive data types. And actually, I'm going to talk in general more about data types for all of us. Whenever you are assigning a value or a data type to a variable, we had this thing that it said that we have the type, and then we have the name, right? The type and the name. So for type, we have 2 options. It can be either a primitive value or an object. Sometimes it just fills in. Or an object. So if we have that primitive or an object, inside of a primitive, we have some very basic data types. And those data types are basically how the computer is allowing us to communicate with the computer or represent the world. So one of those would be an int, for example, which is essentially a number. But it's not only any number, it's a number that it's complete. So there's no fractions. The other one would be, the basic one would be a float, which is another number, but with fractions. There's a byte, which is binary data. We have a Boolean, which is yes or no. We have a character, which defines a single letter. And I think that's basically it for now. Yeah, I think that's it. Let me just, because at the very least from the perspective that I want to show it. So these are the very, 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 very basic primitives. But the ones that are in this category of numbers, whether they're integer numbers or floating point numbers, we have either from a small memory footprint, we have a large memory footprint. And same thing for this one. Well, we already have float, and so I'm actually going to say that the only other one that it's around this, because there's no tiny float or anything like that, but it's large memory footprint. 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 Okay, so we've got different kinds of memory footprint. Why would this be important? Because languages like Java were written a long time ago when considerations about how to utilize your memory were a lot more taken into account. So if you have, certain operations and you have a certain amount of memory and a certain amount of RAM, you might want to not represent an integer that is going to be from 1 through 10 with an int. And the reason is probably better depicted here, because the int utilizes 4 bytes. And with those 4 bytes, it can go from minus 2 billion to 2 billion on the range of the numbers that it can support. So might better be using a short, which goes from minus 32K to 32K. Now, let's talk a little bit about that part, because what does it mean that we are using this the size of the memory? Let's assume that since we remember that everything in memory is like light switches, where we have all the way to 64. There would be 64 bits. And this is where probably those of you that have heard like, oh, this is a 64-bit version, is that any number on an integer, in this case, would be using 4 bytes, which would be, would utilize more, because in case that you wanted to represent something really big. So in the case of an int, we had it in here, it goes from minus 2 billion to 2 billion. So why is it going from minus 2 billion to 2 billion? So an int has a 4 billion range. And by using that 4 billion range, rather than going from 4 to 4 billion, we are sliding this scale to go from minus 2 billion to 2 billion. And the idea behind that is because there's a lot of times that you want negative numbers. So from that 4 billion range of numbers that can be represented, we're putting it in the middle, rather than starting like this, and where you have 4 bil and 0. It's preferable per the Java guys to map the end to this and map the beginning to this, and somewhere in the middle goes the 0. Basically, if we were going to choose something else, it's just for pure efficiency purposes. So if we are looking at this table, we're going to see that, for example, a short goes from a smaller range, therefore it won't use as much memory. But if you want to go something past 2 billion, so for example, you want to assign an ID for every human being on the planet using a long, you can do it. And the same thing goes between a float and a double. For example, if we wanted to just do an approximation of pi, we could just leave it like that, and that would be a floating point number with a limited amount of data. But if we go towards a bigger solution, let's assume that we want to calculate really deep into pi. So for example, pi value, and there's got to be a web page. Actually, this one is really interesting because it has all these digits of all the calculations of pi. You can see how there's so many digits after that 14952. And in my own version, it was 3.14159, let's assume 2. And so that's the difference between a float that it's using less memory footprint versus a double that it's using a lot more footprint. A character is an interesting one that in the case of Java. Because Java has what it's called a literal, which if you use a single quote, it will treat it as an integer. As a char. If you use double quotes, it will be a string. The string literals, and in this case character literals, is if you have a variable defined like C, that is going to be a char, and if you have it like this, that's going to be a string. And we're going to be talking about strings in the next class. So I just want to highlight the fact that in a char, because it's in a single quoted, also because it interprets it as a char rather than as a string, you can only have one single character. Then we have booleans who just do yes or no. That's a boolean. Then just yes or no, and that's a boolean. And then we also have bytes, which represent data that it's non-human readable. So let's say that let's assume that we write that, okay? Float x equals 13. And that would actually go well. Actually, let's even give it a go. It would be that would actually compile it, even though that it's saying that it's never used. But it would compile the code. But a float technically is waiting for a 0 or like an X format number, where X is a number of digits and here is also a number of 6 digits. Because we don't have that floating point, the compiler will try to cast it immediately. And if it can. So in some cases, like this 13 going from a 13 into a float, what it's going to do is that it's going to turn it into 13.0. Because the 0.0 is exactly the same as this one. It's just, we don't have that that rounding of the number. So it can automatically cast that variable. So casting, since we're bringing it up, casting is the process of us converting from one data type to another. Then what happens when we are trying to convert from, let's say, int x equals 5.6, something like that. If we assigned the value 5.6 to the variable x, we would get a compiler error. And the reason for that is very simple. How are we going to drop this value Should we round up? Should we round down? Should we just exclude it? How are we going to do it? So Java tries to discourage anything that is not predictable from being done. And so in this case, the compiler might give us a warning. So why don't we try that? Why don't we go into our IntelliJ and type int x equals 5.6. And why don't you guys try to type it in your IntelliJ and tell me what is the error that you guys are seeing. Okay, error incompatible types. Yes, incompatible types. And that is because the compiler, even if we say, so this is the syntax for changing or casting a value, forcing the casting of a value. If I do this, I am explicitly telling the compiler, you know what? I don't care what is this previous value. I want it to be converted into an int. So what it's going to do is that it's going to grab that 5.6 and essentially drop this guy. But that is once you actually say, I really want it as an int. It's going to drop everything after the floating point. But again, that's when we have to force it. So again, it's easier to fill in zeros when necessary than to removing something. And the example that I like to use whenever we're casting to understand why casting like that is not done by default. Imagine if I told you guys, hey guys, good news. We're all going to get $0.9 million casted to an int. Dropping the precision, it's a big deal when it's a big number, right? So that's why Java doesn't really automatically drop the percentages, because a lot of people might be like, what's the big deal between 10 and 10.5? It's whatever. But if I told you a bigger number and say $0.9 million casted to an int, well, you're getting nothing. The next thing that we're going to do, that we're going to review then, is understanding comments. Comments get stripped out, as well as extra spaces. So spaces are free in your code, so you can add any extra spaces, white spaces, to make it visually appealing to you. But once it's compiled, all those white spaces, all the comments are removed, and it doesn't make it into the actual compiled file. The most important thing that a programmer should do is to communicate with another programmer. So comments allows somebody else to come back in and read the code and understand what they're doing. So if we do like this line, let's say do not delete or modify below x plus plus blah blah blah. So you know, like this line below, like the comment is basically telling you something useful as a programmer. This is a single line code. I don't have to close the statement. But what happens when I have something bigger to write? I need a multi-line comment section, so I can start saying, if it's going to start looking for anything that is between these two / star */. So for example, I can start putting, this was written by Juan Carlos Moreno, and this is awesome, and this is great, and all my students rock. This is basically a multi-line comment. The comments close when I close it down here. I didn't have to do it on each line. That is particularly useful for documentation and things like that. And there's actually programs that read the code and build documentation files out of comments in methods. So comments are something very simple. It's just notes for the developer.